Hello everyone, thank you for joining me in the discussion of my co-op project, Alarm Optimized HMIs. So what is an HMI? HMI stands for Human Machine Interface, and it is simply the user interface that connects an operator to the controller for an industrial system. This discussion will focus on the graphics associated with an HMI. When computers were first introduced to the industry to begin controlling processes remotely, HMIs were an integral part of that migration. One of their primary functions is to deliver key performance indicators to the operators, indicators such as temperatures, pressures, and flow rates. Using these indicators, operators can monitor their processes remotely and respond to any alarms that might appear. Over the years, however, a detrimental problem began to surface across the industry: the inadequate management of alarms. Safety incidents began appearing across the globe. In Milford Haven, 1994, an explosion occurred at the Texaco refinery when 20 tons of flammable hydrocarbons escaped the knockout drum, forming a vapor cloud that eventually found a source of ignition. In Pennsylvania in 1979, the 3 Mile Island Unit 2 reactor partially melted down and released radioactive material, causing the evacuation of 140,000 citizens and a cleanup cost of approximately $1 billion. And hey, maybe you remember the worst industrial accident in history: Bhopal, India, 1984, where thousands of people died from a Union Carbide plant's leakage of nearly 42 tons of methyl isocyanate, a highly toxic gas. These events and dozens of others have one major contributing factor in common: the failure of alarm systems. Control systems were overloaded with alarms, causing severe alarm flooding whenever an incident occurred. Operators also faced the challenge of locating the alarms because their HMIs were full of distracting colors and animations. For example, on this HMI, your instinct is to look for red in the same way that a red alarm on your car's dashboard means trouble, but so many objects are colored red that you don't know which to select first. Not to mention, the purpose, priority, and corrective actions for a lot of the alarms in this HMI were not rationalized. Together, these issues called for alarm reform throughout all of industry. As a result, industry leaders like the Abnormal Situation Management Consortium introduced the Standards of Alarm Management, which compel companies to thoroughly examine their control room alarm practices. This is where my project comes in. During my time as a process control engineering co-op, I have been designing alarm-optimized HMIs with enhanced technologies that facilitate these operator needs. The bulkiest part of my project is migrating over 150 traditional HMIs, which utilize OLE for process control, or OPC, to alarm-optimized HMIs, which utilize both OPC and HTML functionalities, using vendor-supplied design software and piping and instrumentation diagrams. In this process, I reserved colors for alarms interlocks only. After I configured the rationalized alarm groups in the servers, the most critical alarm on this HMI became unmistakably clear. I also designed the HMIs to follow a logical left-to-right main substance flow, making it easier for the operators to navigate through the process. Additionally, in an attempt to improve the integrity of the distributed control system, the DCS, I consolidated process data wherever possible to reduce the load on the network interface module, or the NIM, as the information traveled through the channel. For example, in the traditional HMIs, the two discrete inputs 1040E and 1040E1 were invoked separately, causing the DCS to work harder while retrieving the data all the way down at the device switches. When I consolidated the 2 points into a composite, the strain on the DCS was reduced because the composite points read the inputs separately, allowing for the HMI to invoke the information within the controller instead of having to travel so far down the channel. By their very nature, traditional HMIs cause unnecessary strain on the control system because of how they move parameters on a DCS highway. In an audit conducted at my company, one type of traditional HMI called a Global User Station, or a GUS HMI, was found to move 626 parameters every 4 seconds, leaving only 0.11% of the NIM CPU free. The recommended limit? 20%. The total number of parameters per second was found to be 2,937. The recommended limit for that? 1,400. When HTML HMIs were implemented, however, only 121 parameters were moved as needed. The information was transferred only upon receiving new data, instead of forcing the signal down the highway every 4 seconds, regardless of whether the data had changed or not. As a result, the HTML HMIs brought the system's NIM load back into recommended limits, leading us to the conclusion that GUS HMIs are not reliably reporting critical information. Finally, one of the most important enhancements that HTML offered was the right-click functionality for readily available alarm information. Previously, when a point went to an alarm, operators had to flip through a giant binder of alarm information. This method took a lot of time and didn't always work because the binders were often out of date. By leveraging the alarm database and Microsoft Access, I customized a script that enables operators to immediately view the most up-to-date alarm information with 2 clicks of the mouse. Now, all the operators have to do is navigate to the point in alarm, right-click, and select Alarm Help to invoke a one-pager of alarm information. Additionally, whenever an engineer updates the alarm database, the updates are replicated down to all operator consoles. I cannot stress enough the differences these alarm management efforts have made in the industry thus far. In one of my company's most active control rooms, the average number of alarms per week totaled approximately 9,036 before the process of alarm rationalization. After implementing the Alarm Rationalized database, the number of alarms was brought down to 1342, when hundreds of nuisance alarms were eliminated or reprioritized, creating an 85% reduction without sacrificing critical alarms. Additionally, the implementation of alarm-optimized HMIs has led to better detection of abnormal situations before they occur, better success in responding to abnormal situations, and better completion time in handling abnormal situation tasks. With these large alarm management efforts, we are striving for 0 incidents, 0 injuries, 0 fatalities. We are striving for 0. Thank you.